Hello and welcome to online lecture number 9 for Chemistry 112 during the spring semester of 2020. In this lesson, we're going to start a new chapter, chapter 17, and to do so, we're going to introduce oxidation numbers. So electrochemistry is the field of chemistry interested in the interconversion between chemical energy and electrical energy, converting between those two types of energy. And electrochemistry is very important. Electrochemistry is the kinds of chemistry that powers all of our batteries. Imagine what our life would be like if we didn't have a portable source of energy in these batteries. In order to produce electrical energy from chemical energy, we have to use chemical reactions, spontaneous chemical reactions, that involve a transfer of electrons. And these chemical reactions that involve a transfer of electrons are redox reactions. So essentially, electrochemistry is one of the many applications of those oxidation reduction reactions, those redox reactions that were probably first introduced to you in Chemistry 1. So in Chemistry 1, Chapter 4 in our textbook, we introduced this as an example of an oxidation reduction reaction. Copper 2 plus ions can react and will react spontaneously with elemental zinc to produce elemental copper and zinc 2 plus ions. Consider this reaction is to break it up into two half reactions, where in an oxidation reduction reaction, we have both something being oxidized as well as something that's being reduced. And one convenient way of better understanding this overall redox reaction is to break it up into two half reactions. One just describing the oxidation process, where zinc, elemental zinc, is going to zinc 2 plus with the loss of 2 electrons. And then the second is called the reduction half reaction, which just describes the reduction process, where the copper 2 plus ions are then gaining or accepting those lost 2 electrons to produce elemental copper. Notice that the sum of the two half reactions will give us the overall reaction. And we want to kind of keep in mind as we go through this chapter what we mean by oxidation and reduction. One mnemonic we can use is oil rig. Oxidation involves loss of electrons. Reduction involves gain of electrons. All redox reactions have in common is that they involve a change in oxidation number of 2 or more elements. So we want to spend an entire time today just reviewing what we mean by oxidation number and how to determine oxidation number for any element in any compound. So oxidation means we have an increase in oxidation number, whereas reduction means there's a decrease in oxidation number. So if we're able to, for any given reaction, determine the oxidation number of the atoms on the reactant side and product side, whichever atom's oxidation number increase, we say has been oxidized. Whichever atom's oxidation number has decreased, we say has been reduced. So with oxidation numbers, oxidation number, also sometimes referred to as oxidation state, describes how the electronic environment of an atom in a compound compares to an electron environment as an element. So it's essentially a electron bookkeeping method to compare how many electrons, how many valence electrons specifically, does this atom have as an element, what it was kind of created with, compared to how many electrons, how many valence electrons does this atom now own now that's part of a compound. So there's various rules we can follow depending upon what type of substance we're dealing with. So the first rule, the simplest, is that elements, helium, for example, helium, sodium, the diatomic elements, the happy 7, their oxidation numbers are always equal to exactly 0 because these are not part of compounds. So in other words, they still have exactly the same number of valence electrons that they started with. For ionic compounds and for monoatomic ions, so ions composed of just one atom, it's also a simple relationship. The oxidation number of those particular atoms is the same as the charge of the cation or anion. So for example, potassium bromide, the charge of potassium in this potassium bromide ionic compound is +1. So therefore its oxidation number is also +1. Likewise, bromide is -1, which is why its oxidation number is also -1. And we do the same thing for strontium nitride. Strontium is +2, nitrogen is -3. And then for something like a monatomic ion, like the sulfide anion, S2-, because it's a monatomic ion, its charge is the same as its oxidation number. For those covalent, or sometimes referred to as molecular compounds, determining oxidation number gets a little bit more complicated Because for molecular compounds, these are compounds composed of two or more neutral atoms that are covalently bonded to one another. So they don't have an actual charge to them. Individual atoms don't have a charge, they're neutral atoms. The idea here, though, is that the oxidation number is the charge of this atom if the polarization of all non-homonuclear bonds were complete. So in other words, if we have a particular molecule such as water, and we could draw it this way, but we recognize that this covalent bond between hydrogen and oxygen is polarized, that the electrons actually are going to spend more time, so to speak, closer to the oxygen than they were the hydrogen, because oxygen is more electronegative than the hydrogen atom is. So maybe a better way of representing this molecule structure is this way, showing that these shared electrons are spending more time or more closely attracted to the oxygen atom compared to the hydrogen atom. So as a result, take a look at this picture compared to these number of valence electrons the atoms have normally. Hydrogen normally has one valence electron. In this picture, though, it can't claim ownership of any. So it has as a result, it has a +1 oxidation number. It normally has one electron, it doesn't have any, so that difference gives us a +1. Whereas oxygen normally has 6 valence electrons, but in this picture, because it's able to claim ownership of both shared pairs as well as its 2 lone pairs, a total of 8 valence electrons. It normally has 6, it now has 8. It has 2 more valence electrons it normally would have. As a result, its oxidation number, its so-called charge, would be at -2. Likewise, for CH4, same idea. Carbon bonded to 4 hydrogen atoms. These would be considered nonpolar bonds, but even though they're nonpolar, carbon is more electronegative. So if this polarization were complete, then the picture would look like this. Hydrogen would still be a +1 for the same reasoning for water. Carbon would have normally 4 valence electrons. It now has 8, so it has 4 additional electrons than it normally would come with. So as a result, it would have a so-called charge or oxidation number of -4. And then with HCN, we have this structure. We could also write this way because carbon is more electronegative than hydrogen, so it gets to claim ownership of both of these shared electrons, but nitrogen is more electronegative than carbon, so it gets to claim ownership of all 3 pairs that constitute this triple covalent bond. So as a result, hydrogen has a +1 oxidation number. Carbon normally has 4, now it can only claim ownership of 2, so it has a +2 oxidation number. And nitrogen normally has 5, it can claim ownership of all 8, so it has oxidation number of -3. So this is really the real rule for determining oxidation numbers of molecular compounds. Fortunately, though, there is a sort of a shortcut. And the shortcut is based upon this very important idea that when we add up all the oxidation numbers of all the atoms in a molecule or an ion, that sum must equal the charge on that molecule or ion. We can see that, for example, for water, we have 2 hydrogens, +2 for the 2 hydrogens, plus a -2 of the oxygen, gives us a charge of 0, a total of 0, which matches the 0 charge of the water molecule. So taking advantage of this very important rule, we can come to a shortcut to determine the oxidation numbers of these non-metal atoms as part of these molecular compounds without necessarily having to draw the structures and thinking about the electronegativity differences. To do that, we're going to use this table. This is a table of priority, in that elements listed higher in this table have higher priority, have higher preference of their oxidation number compared to elements lower in the table. So how we would read this table would be that fluorine, if it's part of a compound, so these are only relevant when we're dealing with elements as part of a compound. When fluorine's part of a compound, it's going to have an oxidation number of -1. When hydrogen is part of a compound, it's going to have an oxidation number of +1 unless that conflicts with fluorine's preference. Oxygen would like to have an oxidation number -2 unless that conflicts with hydrogen or fluorine's preferences, and so on and so forth. So we can then use this table and then use this rule to determine oxidation states of these other elements. So I'll go through a couple of practice examples. So for zinc, notice that zinc is a monatomic ion. As a result, the charge of a monatomic ion is the same as the oxidation number, so zinc would be +2. Nitrogen is an element. Because nitrogen is an element, that means that the charge, the oxidation number rather be 0. But then for these others, we have to maybe do a little bit more calculations to determine what the oxidation numbers might be. Okay, so for CH3F, applying our number 1 rule here, we have 1 carbon, 3 hydrogen, and 1 fluorine. And so we could say that the sum of the oxidation number of 1 carbon plus the oxidation number of 3 hydrogens plus the oxidation number of 1 fluorine, that must equal the charge on the molecule. There's no charge indicated, so we know as a result the charge must be 0. So then we apply our priority table. We don't have a rule regarding carbon. Carbon's a group 14 element. It's not part of our table, so we don't know what carbon is. Hydrogen, though, it wants to have an oxidation number of +1. Prefers to have an oxidation number of +1. And fluorine prefers to have an oxidation number of -1. So that sum must equal 0. So we have 1 carbon plus 3 plus a -1 equals 0. We have 1 carbon plus 2 must equal 0. 1 carbon equals -2. And then finally carbon, then as a result, must have an oxidation number of -2. And so we can determine the oxidation number of, in this case, carbon, because when we add up all the oxidation numbers of all the elements, it has to equal the charge. So if we know from the table what hydrogen and fluorine's oxidation numbers will be, we can deduce then what carbon must be. So carbon would have a -2 oxidation number. Hydrogen's +1 and fluorine's -1. So then we'll do the same thing for the carbonate ion. So carbonate, CO3, 2-. We have, from the formula, 1 carbon and 3 oxygens. So the sum of the oxidation numbers of carbon and 3 oxygens must equal the charge. The charge is -2. So we don't know anything about carbon, but we know oxygen prefers to have an oxidation number of -2. So we have 1 carbon plus -6 equals -2. As a result, 1 carbon must be equal to +4. In other words, carbon must be equal to +4 oxidation number. So carbon has an oxidation number of +4 in this structure. And oxygen has the preferred oxidation number of -2. With the ammonium ion, NH4+, we have nitrogen. We have 1 nitrogen. We have 4 hydrogens. And the sum of their oxidation numbers, according to our number 1 rule here, must equal the charge, and the charge is a +1. We have nitrogen, hydrogen. There are rules regarding both nitrogen and hydrogen. Nitrogen is a group 15 element, so it prefers to have an oxidation number of -3, but notice that hydrogen is higher in this priority table. So we're not necessarily going to conclude, necessarily predict that nitrogen will have a -3 oxidation number. We may calculate that way, but we want to first say that hydrogen, because it's higher in the table, is going to have a +1. So we'll treat our nitrogen as our unknown, in other words, to see what it actually turns out to be. So 1 nitrogen plus 4 equals +1. And so therefore 1 nitrogen equals -4. So it's 1 minus 4 is -3. So in this case, nitrogen does in fact have its preferred oxidation number as a member of group 15 of -3. We could also prove that based upon the fact that when we add up all the oxidation numbers, it must equal the charge on the molecule and ion. So nitrogen -3, hydrogen +1. And then 2 more examples, PCl5. So PCl5 composed of 1 phosphorus atom, group 15 element, and 5 chlorine atoms. And we add up the oxidation numbers, must equal to charge. The charge is 0. So the sum of the oxidation numbers must also equal 0. So we have rules regarding both phosphorus and chlorine. Chlorine's group 17, phosphorus group 15, but group 17, chlorine, is higher in this priority table. So I'm going to treat phosphorus as my unknown, and then state then that chlorine will prefer to have a -1 oxidation number. So that in mind, we get 1 phosphorus plus a -5 equals 0. 1 phosphorus equals +5. So therefore, phosphorus would have a +5 oxidation number in this case. So it's not the preferred oxidation number of a group 15 element like phosphorus, but it's the oxidation number must be based upon the fact that when we add up the oxidation numbers of all the elements, it must equal the charge. So a positive 5 phosphorus, a negative 1 for chlorine. And finally, one more example, the triiodide ion. This is the correct formula of that substance, I3 minus. So this ion is composed of 3 iodine atoms. So 3 times the oxidation number of iodine must equal the charge. Charge is -1. As a result, what we conclude is that the iodine atom has an oxidation number of -1/3. And that's an important idea, is that when we determine the oxidation numbers of these elements, we're determining the oxidation numbers of each individual atom. And if a molecule contains more than one of that particular type of element, then strictly speaking, when we determine oxidation numbers by this method, we're determining the average oxidation number. So in reality, if we draw the structure of triiodide ion, the average oxidation number is in fact -1/3. Because the other 3 iodine atoms, the iodine atoms on the ends, they have oxidation numbers of 0. The oxidation number of the iodine atom in the middle is -1. So on average, they do in fact have an oxidation number of -1/3, even though no individual iodine atom has a fractional oxidation number. But we sometimes get fractions because, as I said, these are average numbers. And then one more example. I normally would do this as a class exercise, so I encourage you to take a moment and think about, for hydrogen peroxide, what would the oxidation number of the oxygen atom be in the hydrogen peroxide molecule? So pause the video if you need to, and then we'll go over the answers. So for hydrogen peroxide, we can think about a couple different ways. We can first draw the structure, where we have unequal sharing electrons between the oxygen and hydrogen, equal sharing electrons between, obviously, 2 oxygen atoms, and then unequal sharing electrons between the oxygen atom and the hydrogen atom on the right. Alternatively, we could draw it this way to get a better idea. The hydrogen atoms would have their +1 oxidation number, as we'd expect. The oxygen atoms, though, they normally have 6 valence electrons as elements, but in this particular configuration, each oxygen atom has 1, 2, 3, 4, 5, 6, and then it gets to claim ownership of half of these shared electrons between, in this homonuclear bond, between this bond between the same 2 atoms. So in other words, each oxygen atom originally has 6, it can now claim ownership of 7. So in other words, it now has, in this particular arrangement, it now has 1 more electron than it normally would have. As a result, then, we conclude the oxidation number of each oxygen would be -1. Also, we could also do the other method using our table. So with hydrogen peroxide, we know the hydrogen peroxide is composed of 2 hydrogen atoms and 2 oxygen atoms. So the sum of the oxidation number of 2 hydrogen atoms and 2 oxygen atoms must equal the charge, which is 0. Hydrogen is higher up in this priority table than oxygen. So we would treat oxygen as our unknown, so to speak. So hydrogen is +1. Oxygen is our unknown. So 2 times +1 plus 2 times whatever oxygen is 0, the charge. So 2 plus 2 times whatever oxygen is 0. 2 times whatever oxygen is going to be -2, and divide both sides by 2. It concludes, come to the same conclusion, that oxygen must be a -1 oxidation number. So either using this table or the real rule, which is looking at the structures, we can equivalently conclude that oxygen has a -1 oxidation number. So we kind of reviewed oxidation numbers from Chemistry 1, and then in the next lesson, we'll get into applying oxidation numbers and these assignments of oxidation numbers in order to balance redox reactions.